This is a tutorial on acids and bases. If you need a review of electrolytes, strong electrolytes and weak electrolytes and non-electrolytes, look back at my electrolyte video, because I will assume you've seen that in this presentation. Let's talk about some properties of acids and bases. Acids tend to taste sour and they'll cause dyes to change color. Bases tend to taste bitter and they tend to feel soapy to the touch in many cases. As far as litmus paper goes, the blue litmus paper will turn red if exposed to an acid, and a base will turn the red litmus paper blue. Let's talk about some definitions of acids and bases. The simplest definition is the Arrhenius definition. According to Arrhenius, acids tend to increase the hydrogen ion concentration, where bases increase the hydroxide ion concentration in solution. According to Arrhenius, an acid will react with a base, where the acid and the base will chemically react to form a salt and water. For example, if we react hydrochloric acid with sodium hydroxide, there's your acid and your base. It'll react to form sodium chloride, which is your salt, and water. Problem is that confines us to aqueous solution. There are some more sophisticated or more generic definitions that do not limit us in that way. A little bit more complex definition is the Bronsted-Lowry definition of acids and bases. In this case, the H plus ion is, remember, that's just a proton with no electrons. Where a neutral hydrogen atom has one proton and one electron, but no neutrons, typically for the common isotope. In water, the H plus ion doesn't just simply exist by itself. Usually it forms a cluster with water, the simplest of which is H3O plus, which is the hydronium ion. You can form larger clusters like H5O2 plus and H9O4 plus, so on and so forth. Now, according to the Bronsted-Lowry definition, the acid donates H plus and the base accepts H plus, which means that it need not necessarily have water. It could donate or accept the hydrogen ion without water necessarily being present, which is important if you go into organic chemistry. The Bronsted-Lowry base, in this case, does not necessarily need to contain hydroxide ion, which is important because some bases don't. In this case, if we put HCl into water, we find that we form the hydronium ion and a chloride ion. So instead of forming an H plus and a Cl minus, we end up donating that H plus to water since it's an aqueous solution. So since the HCl donates a proton to the water, HCl would be the acid. Water here accepts a proton from HCl, so since it's accepted the proton, or the H plus, water is the base. Water can behave as either an acid or a base depending on the context. As we'll see, a substance that can behave as an acid or a base is called amphoteric. So let's talk about conjugate acid, conjugate base pairs. Whatever's left of the acid after the proton is donated is the conjugate base. Similarly, whatever remains of the base after it accepts that proton is called the conjugate acid. So if we consider some generic acid reacting with water, we'll get the anion of the acid, A minus, and the hydronium ion. Now, after HA, which is the acid, loses its proton, is converted to A minus, and the anion of an acid, particularly a weak acid, is basic. Therefore, HA and A minus are conjugate acid conjugate base pairs, where HA is the acid and A minus is its conjugate base. Now water acts as a base and gains a proton, therefore it's converted to H3O plus, which is acidic. Therefore, water and hydronium ion are conjugate acid conjugate base pairs, where water in this case is the base and H3O plus is its conjugate acid. Notice the conjugate acid conjugate base pairs differ by one and only one proton. Here's an example. Let's identify the conjugate acid conjugate base pairs in each of the following. So let's look at acetic acid reacting with water to form the acetate ion and the hydronium ion. And so one conjugate acid conjugate base pair is the acetic acid acetate pair, where acetic acid is of course the acid and acetate ion is its conjugate base. And we've got water acting as a base and hydronium ion being its conjugate acid. In part B, we've got ammonia, which is a weak base, reacting with water to form the ammonium ion and the hydroxide ion. Now, ammonia and ammonium ion are one conjugate acid conjugate base pair, where ammonia is the weak base and ammonium ion is its conjugate acid. And we've got water here acting as an acid, where the hydroxide ion is its conjugate base. Note, water behaves as a base in part A, but it acts as an acid in part B, illustrating that water is in fact amphoteric and can behave both ways. Let's talk about relative strengths of acids and bases. The stronger the acid, the weaker its conjugate base is. Hydronium ion is the strongest acid that's going to exist in equilibrium in aqueous solution, and hydroxide is the strongest base that can exist in equilibrium in aqueous solution. Anything that's stronger than that will just react stoichiometrically with water to produce H plus or OH minus. Conjugate base of a strong acid, like chloride, is the conjugate base of hydrochloric acid. Those ions are pretty neutral. Negligible acid-base properties are like sodium ion compared to sodium hydroxide or something like that. And so if you look at sodium ion, it's from sodium hydroxide, which is a strong base and has negligible acid-base properties as well. If we look at this scale, we can see the strong acids are at the top and left. And so you got things like hydrochloric and sulfuric and nitric acid, all fully ionized to form H+. You can see the conjugate bases on the right-hand side. Things like chloride and bisulfate and nitrate aren't bases. But once you get below that box with the H+ and the water in it, the acids on the left are weak. They don't completely ionize, and therefore hydronium ion is less concentrated than for a comparable concentration of a strong acid. And they get progressively weaker as you go down the scale. So you get down to water, which is amphoteric, but the solution is going to be neutral if it's just pure water. And then you got things down below that, like the HS minus and the hydroxide and hydrogen, which don't really act as an acid at all. On the left, you've got your bases where they're pretty negligible at the top and actually very strong at the bottom, with a sliding scale of weakly ionizing bases in the middle. Notice those anions of the weak acids are themselves a weak base. But those bases below hydroxide in the box there on the scale on the right are actually pretty strong bases and will react with water to form some hydroxide. There's a brief review of strong electrolytes versus weak electrolytes. And strong electrolytes will ionize 100%, but your weak acids or your weak bases are going to ionize or dissociate partially, usually much less than 100%, and often it's less than 10%. Strong electrolytes are going to ionize or dissociate completely. For example, if we got nitric acid down there reacting with water, more or less 100% ionization, we get H3O plus and the nitrate ion. Or if you chop the water out and use the Arrhenius definition, nitric acid will 100% ionized H plus and NO3 minus. So if nitric acid is 0.050 molar, we want to calculate the concentrations of the ions. So if we write the equation for the ionization, we got nitric acid plus water forming nitrate, and hydronium ion, notice the one directional arrow, 100% ionization. We'll worry about calculating concentrations of weak acids and weak bases another time. I'll do another presentation for the equilibria of those weak acids and weak bases. But for strong, we're going to assume that since it's a strong acid, we're going to assume the ionization is complete and that the concentrations of nitrate and hydronium ion are 0.050 molar, and therefore are the same concentration as the original concentration of the acid before it ionized, since the stoichiometry is all 1-to-1. The concentration of the acid at the end of the process would be 0, since it all went to form the ions. Calculations involving weak acids and weak bases are going to be a bit more complex, and they'll be equilibria. And again, we'll do that in a different presentation. Now, let's do the same thing for a 0.020 molar solution of strontium hydroxide, SrOH2. Now we got to be a little bit more careful of the stoichiometry here. But the same concept, it's a strong base. It's going to dissolve to form one strontium 2 plus ion and 2 hydroxide ions. So since the strontium hydroxide is a strong base, we can assume the ionization is complete and that the concentration of the strontium ion is 0.020 molar, the same as the original concentration of the base before any dissociation. But since hydroxide, there's a 2 coefficient on that, we're going to double that concentration that we were given and say the concentration of the hydroxide ion is 0.040 molar. That'll be important once we start calculating pHs of these solutions based on the hydronium or hydroxide ion concentration, so it's important to pay attention to that stoichiometry. The concentration of the original base, the strontium hydroxide, would be 0 since it was a strong electrolyte and completely dissociated to form the ions. Just to review, these are the 7 common strong acids: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric. Chloric is sort of borderline. Perchloric is a strong acid. Those are the strong. If they're not on the strong list, you can assume them to be weak. Similarly, you can say very similar things about the strong bases that are common. We got lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Then we got calcium hydroxide, strontium hydroxide, and barium hydroxide, although the group 2A metal hydroxides are significantly less soluble. But note, they are the group 1A metal hydroxides and the heavier group 2A metal hydroxides. Many hydroxides are not very water soluble, which is why many of them don't act as strong bases. They just don't dissolve in water significantly enough. Many of those bases are called sparingly soluble bases. Let's talk a little bit about water, because most of our acid-base chemistry that we're going to talk about is an aqueous solution. Pure water will ionize very slightly. The concentration is less than 1/1,000,000th molar at room temperature. So we write autoionization of water as a dissociation reaction similar to those that we've done previously with equilibria, where two waters will react with one another, form hydronium ion and hydroxide ion, but that equilibrium is very reactant favored. Very little of the product is formed. Because the activity of pure water is 1, we can write the equilibrium constant Kw for this reaction, where Kw is equal to the product of the hydronium and hydroxide ion concentrations. At 25 degrees Celsius, we're going to say that the hydronium and hydroxide ion concentrations are 1.0 times 10 to the negative 7th molar. But that's at 25 degrees Celsius, not every temperature. And so we can determine Kw from that. And so since it's the product of the two concentrations, 1 times 10 to the negative 7th times 1 times 10 to the negative 7th is 1.0 times 10 to the negative 14th. And that is a constant Kw, which we'll be using in this chapter, but it's good at 25 degrees Celsius. Let's talk about pH. In most solutions, the H plus ion is quite small, but it could theoretically be high. So we're going to define pH as the negative log of the hydrogen ion or hydronium ion concentration. But that's a log base 10, not a natural logarithm, so be careful. Similarly, pOH is the negative log of the hydroxide ion concentration, and really you could do it for anything. If you want to take the negative log of the concentration and just make it a p-type function, it really works for just about anything. So neutral water, the pH equals the pOH, which is equal to 7. Acidic solutions, the concentration of the hydrogen ion is greater than 1.0 times 10 to the negative 7, so the pH is less than 7. In basic solutions, the concentration of the hydrogen ion is less than 1 times 10 to the negative 7, so the pH is greater than 7. The higher the pH, the lower the pOH. So you can take those same statements I said for hydrogen ion and reverse them for hydroxide ion. Most pH and pOH values fall between 0 and 14, although there's no theoretical limit. pH of 2 molar HCl is negative 0.301. You're going to hit 0 at a 1 molar concentration of a strong acid. You're going to hit 14 in the pH for a 1 molar solution of a strong base. Let's talk a little bit about relating pH and pOH using the autoionization of water. You can write them directly. If we start with our autoionization of water equation, where we've got the hydronium times the hydroxide equals 1 times 10 to the negative 14th. If we take the negative log of both sides, we get the negative log of the Kw equals the negative log of the product of the hydronium and hydroxide ion concentration, which equals negative log of 1 times 10 to the negative 14th. Separating the hydronium and hydroxide using the laws of logs. If they're in the argument, it's the same as adding them together, but there's a negative out front, so that middle term becomes negative log of the hydronium ion concentration minus the log of the hydroxide ion concentration. Now negative log we know can make the p-type function, so we find that forms the pKw because it's the negative log of the Kw equals the pH plus the pOH, and we find that that sum equals 14. And that's where that comes from. Here's just a basic schematic showing pHs of common things, so that you have an idea of what the pH scale really is. You see I've done the pOH. Notice that those scales are inverted, pOH versus pH. And if the hydrogen ion concentration is big, the hydroxide ion concentration is small, and vice versa. But you can see 0.1 molar sodium hydroxide comes in at a pH of about 13. Household bleach, maybe about 12.5. Ammonia, a little less than 12. Lime water, close to 10.5. Milk of magnesia, slightly less than 10. Baking soda, maybe 8.5. Seawater, a little less than 8. Human blood, it's usually about 7.4. Rain, now we're not talking acid rain, but just with normal atmospheric gases in it, a little less than 6. Black coffee coming in about 5. Soft drinks and vinegar about 3. Lemon juice slightly above 2. 0.1 molar HCl is pH of 1. So let's work some of those calculations involving pH and concentration of ions. We'll do that for a 0.2 molar nitric acid solution. Since the acid's strong, the concentration of the nitric acid initial is equal to the hydronium ion concentration, which is equal to 0.020 molar. So we can get that without calculation. We just need to calculate the other three. So the pH, since I have the hydronium ion concentration, is negative log of the hydronium concentration, or negative log of 0.020, which is 1.7. Now, we had our Kw equation, so we can solve that for hydroxide and get the hydroxide ion. So hydroxide ion is equal to Kw divided by the hydronium ion concentration, or 1 times 10 to the negative 14th divided by 0.020, or 5.0 times 10 to the negative 13th molar. Notice the hydronium ion was kind of big, so the hydroxide ion concentration is small. That you should see that, or the answer is not going to be right. Now we also know the pH plus the pOH equals 14, and so we can use that and say, well, the pOH is equal to 14 minus pH, so 14 minus 1.7 is 12.3. Here's another one. We calculate the hydronium ion, the pH, and the PO, or the hydroxide ion concentration for a solution with a pOH of 8.69. So pH plus pOH is equal to 14. So pH is equal to 14 minus pOH, so 14 minus 8.69 is 5.31. Now the pOH is the negative log of the hydroxide ion concentration, so to get the hydroxide ion concentration, do a little algebra. So hydroxide ion concentration is 10 raised to the negative pH, or negative 8.69, which ends up being 2.00 times 10 to the negative 9th. And so what's left is the hydronium ion concentration. So hydronium ion is equal to Kw divided by hydroxide ion concentration, or 1 times 10 to the negative 14th divided by 2 times 10 to the negative 9th, which is going to be 5 times 10 to the negative 6 molar. This has been a tutorial on acids and bases, including pH.